for inviting me here. I'm actually here for the SC Asia, so I'll give 2 keynote talks, one tomorrow and the day after, one another day after. But then Ganeshan said, okay, why can't we put this? I said, that's fine. But I had to take it, like, I just landed today morning, that's why I saw you in the morning talk. So as most of you know, I don't have to tell you, like we are seeing a lot of growth in high performance computing. In that context, So when we're talking about like HPC, as you know, like it's not just a simple compute cluster, we also have storage cluster, we also have the multi-tier data centers. So this is where we see like people are trying to integrate systems over local AI network or the wide area network. So this again means many of you know, means we are in a very exciting phase. So if you see like 2017 we were 100 petaflops, in the latest summit we did 143 petaflops. And of course, the community is heading to the hexaflop. That's the kind of the goal we want to achieve, either at least in the 2021 or 2022, depending on which country we'll be trying to be. Now, if you look at the internals, these are the basic components. As you see, the multi-core processors, the standard x86, and now OpenPOWER is a candidate. Also, is coming up. A lot of multi-core processors are coming, and of course, InfiniBand. That's the kind of the network which is driving almost the last 18 years now. In fact, today morning there was a note, I don't know whether NVIDIA is trying to acquire, Alan, did you read that?
NVIDIA now?
NVIDIA.
Oh.
Somebody's always
Oh, that's a rumor. Sorry, we should have
You may hear that tomorrow. I don't know. I got some notes. So.
There were talk about Intel.
Yeah, Intel, I gave some time also, but I think this is heading into.
Looks like all OpenPOWER partners now will be acquired by competitors, looks like.
Yeah. So, and that's the latest I got today morning. It was $7 billion NVIDIA will purchase now.
1 billion more.
Yeah. And then of course we have the accelerators. But more important thing also, I think some of you might not be knowing, this is the new direction which is coming. The NVMe SSDs, basically the whatever InfiniBand brought, like the RDMA mechanism kind of things, is now also going to the storage. So audio like, I'll go into a little bit more details, like the GPUs and InfiniBand were connected together. It's like GPU direct RDMA, so if you want to send data from GPU to network or network to GPU, you don't have to go through the host. You can do it over PCI Express. That kind of knowledge is being extended to these NVMe SSDs. So if I have an SSD here, I can directly write data from a GPU to the SSDs over the network. I don't have to go to the host. So in the next few years, you will see a lot of changes to the IO subsystems design of all these systems. So this is a very quick overview. If you would have been working in this area, at least I work in this area, the networking, if you see like Ethernet started in 1979, gradually there was a growth up to 1994, but then this is the second wave started. The internet, how many of you are familiar with it? So it started from 2 gigabits and then continuously went up, and then now we are at the HDR. That is 800 gigabits per second. So effectively, if you see, there has been like 100 times the network bandwidth has increased in the last 17 years. So that is leading to a lot of excitement in how you design all these kind of systems, so HPC, big data, deep learning, because whatever people used to think communication as a bottleneck, now you may have a creative solutions where that may not be the bottleneck. But of course, bottlenecks are always there. You cannot design a system without any bottlenecks. But at least you move ahead, and then again the next bottleneck comes and you try to solve it. So this is a very quick overview of InfiniBand, currently in the latest number 18. You heard about all the summits, Sierra. In fact, the number 3 system in China, it is actually the InfiniBand system. It's not listed in the top 500 list. It says proprietary, but if you read all the details, it's more different than InfiniBand. It's exactly the InfiniBand network you use there. So like this, if you see, just like in the top 50, there are like 19 such systems are being used. So in this context, like we are the very first one I introduced, like when InfiniBand came in 2001, we were the very first group you have an NPI engine running over increment. That's the MHP's project, which is continuing until 19 years now. I'll talk about that. But before I go, I want to outline some of these challenges. Like people want to design this convergent software stack where you can have HPC, big data, and deep learning today. A lot of people have been talking, but in my group, actually, we have done that. In the last 7 to 8 years, we have the software stacks, people are actually using it. That's what I would like to indicate. Then I'll introduce these 3 major projects. That's the MHP's project, which is MPI and TGAS, not only on the host, but also with CUDA awareness. Then we have high performance deep learning, and then high performance with data analytics, and then I'll close a little bit about this commercials. So this is the kind of picture I always say that these 3 subfields are actually trying to coexist, but at the same time also challenging each other. What I mean by that? So that means you have a HPC system, of course big data runs on this, and if you have a very good solution, people are trying to look for more power. Okay? So then from the HPC big data, then you are going to deep learning, so we are in a very positive cycle. So I tell my students, doesn't matter in which area you work on, as long as this is like economy, we are in this positive cycle, everybody will have guaranteed jobs for the next 10 to 15 years. So that is the kind of like the convergence I'll be talking, and of course this convergence you can achieve on a dedicated system, or you can also achieve in the cloud. So today I'll just focus mostly on the dedicated systems, but we have also solutions for that. So what do I mean by this convergence? So many times what happens in many organizations, you would have seen, like I have a HPC cluster here, there is a big data system here, there is a deep learning system here. Those are good, people try to specialize, but then if you have some workflow, which is trying to involve all 3 components, then you have to keep on moving the data. And this is where we see, if we keep on moving the data, you will lose the performance. So the goal, what we have taken for the last several years in my group, saying, let's say you have a vanilla cluster, a physical compute node, you have some resource manager, third or Slurm, you can have some file system, cluster or GPFS. Can all these jobs run concurrently on the same system? Okay? So it is not just like MPI jobs are running, you can also run Hadoop job, you can just go through the Slurm, you submit it. The same thing, Spark jobs you can submit, deep learning jobs you can submit. So all the data sits in the common file system, so anybody can come up with very interesting workflows and you will be able to get very good performance. So that's the kind of objective I want to put, and I'll gradually show how we have solved this. So then this is the MHP's project I outlined earlier, but before we go into that, as many of you know, programming models. And anytime we come to HPC, what is the programming model we want to do? MPI has been there, I think you indicated MPI has been there for many years. You get shared memory, this is cache coherent shared memory. That is within the node. And in fact, as more number of cores are coming on a single node, that is actually becoming very important. A lot of communications are happening within the node. Okay, so one has to actually optimize that. But then the field is moving into this partition global address space called TGAS. Okay. So that is a new direction where people are saying that we can have the similar kind of memory, but we are trying to provide logical shared memory abstraction on top of the distributed. Okay. So that means it is not cache coherent. Like cache coherent, you know, I can write, you can read, invalidation will happen, all the hardware will take care. That is very hard to do it in a million processes. Okay. But as long as I can do a get and put, like I can go to your memory, read the data, or I can write to your data, but some kind of a upper level synchronization mechanism needs to be done, but that is left to the end users. So this is where a lot of newer kind of things are come. Over the years, I think Global Arrays has been there, UPC has been there. The one which is taking a lot of momentum is OpenSMEM. So that is the kind of the bigger programming language which is coming. So the way in my group we try to do, like how we design this communication middleware. So I just introduced MPI and TGAS as the programming model. You can also think of CUDA, even basic OpenMP, even Hadoop, MapReduce, Spark. So this is where like the middle layer, you can think of it as like an abstraction. If you remember like our instruction set architecture. Instruction set architecture is an abstraction which separates out what user wants versus what the hardware designers can provide. So same thing I see here, like these are the programming models, and if I take a look at the very bottom, I call it like from my group's perspective, I call like a supply side. That means continuously better and better networking technologies are coming, multi-core, many-core, accelerators are coming, and all of them have good features. So how do we take those features and mechanisms into account and then pass it through this programming model, and the end objective is actually the application of the performance. That's what matters in that. Doesn't matter whatever you do, but if you don't deliver the performance and scalability at the application level, then not. So this is where in my group, almost like 30 years, we have been working on these communication libraries for all different kinds of systems, and I'll be talking here how best you do point-to-point communication, collective communication, energy-aware protocol, synchronization, IO file system, fault tolerance. So everything goes into those libraries, and those libraries again can be for pure HPC, for big data, or deep learning, or for convergence. So that is a layered manner. Of course, there are a lot of work also gets done, which is done in a co-designing. So that means we are actually trying to make some changes here versus changes also to the programming model, and might be sometimes the application can also be modified. So if we work on some of those co-designing, then we might be able to get even better performance. Okay, so that is also there. So if you take a look at then this high-level question, saying especially for HPC, I introduced like API has been there, but many people still believe that there is some other component, that is X, that is generally being called. It could be very simple as MPI OpenMP, or it could be MPI plus PGAS. Doesn't matter, nobody knows how the field will work. But these are the kind of the wish list. If you are a library designer, what you need to do is you need to provide like scalability for million to million processes, highly efficient internode communication, both two-sided, one-sided. You need to actually provide a good scalable job starter. This is, many people ignore that, but think of like the summits and Sierras, when you have so many like millions of code just to start an MPI job, that becomes a big challenge. If starting the job takes 30 minutes, I mean, you cannot really use this machine. So there's a lot of actions are taking place there. The other thing is what is happening, a big challenge is the memory footprint. So as many of us know, like the number of cores per processor are increasing, or per node are increasing, the amount of memory is also increasing, but if you do a quick math, the amount of memory per core is decreasing over the years. Okay? So that is putting a lot of challenges onto people like me or anybody, any other organization, saying how do you design these libraries? And many times, in the library, if I provide a lot of buffers, a lot of queues, a lot of interesting data structures, I can do a good performance. But then if I come back and say, look, my MPI library is taking 80% of your memory, you will not be happy, right? Because it's only 20% is given to the end application. But on the other hand, if I flip it around and say, look, I can give you performance, but it's only 20% of the memory, you will be very happy. So those are the kind of the techniques we have been trying to do over the years. And then of course there's a lot of collective communication. I'll go into a little bit more details later on. Then as the number of cores per node are increasing, it's just like a freeway subsystem. If you have like different cities, how do you connect them together? There is a lot of communication happening. Like let's say intranode and internode, you need to balance them. So within the node, let's say I have 128 cores, or very soon you will see 256 or 500 cores. And all of them are trying to communicate outside. How do I handle that? If I don't handle that properly, then I'll again be choked. Then there are a lot of work on happening efficient multi-threading. How do we provide some integrated support for accelerators, fault tolerance, QoS, programming model, virtualization, energy awareness. So these are kind of the big list. So this is where, like prior to InfiniBand, many of you might be knowing, I mean, the systems were using Virinet, Quadrix. I don't know how many of you know those technologies. So in my group, we were working in all those areas. When InfiniBand came, we were the very first ones to jump into, because we knew how the runtime system and MPI gets designed. So in fact, we had a very first, our Environment version was introduced in supercomputing 2002. People saw that, yeah, you can actually connect InfiniBand, make a cluster, and then run a very good performance. That was, of course, with MPI 1. But over the years, I mean, it's not only we have extended to all the like MPI latest standard, also all the other interconnects like Omnipath, Ethernet, Rocky, etc. We also have different versions. I'll touch a little bit about that. So this is a project which is continuing for 18 years now. And so currently it's being used by more than 2,900 organizations in 86 countries. Okay, so these are based on voluntary registration. A lot of people just download our things, that is fine. There is a form there if you want to identify yourself, if you are using, then that is the kind of things. You can go to the users list there and see. So just last supercomputing time, like in the November, we crossed 500,000 downloads just from our site. Okay. Of course, it's a part of a lot of other vendors, Red Hat, HPC, OpenHPC, we don't keep track in the vendors. But not only just the download counts, I mean, we have been here for almost like over a decade trying to enable these kind of systems. Like earlier you met Shubhami, I think you mentioned, other person mentioned. So over the years we have been working, like this is actually the Sunway Tile Light uses our things, over stacks, Country 2, Panda, so all these task systems you'll be seeing MRPs is running there. And of course there is a new system which is coming up in US, I don't know how many of you have heard of, Frontera system. It is from Texas Advanced Computing Center. That is a pure InfiniBand system, SDR and the regular x86. So there is no exotic architecture, but I am a OPI there. I think there is a keynote talk in the SC Asia, Dan Standing from TAC, will be in 2010. So this is being put together, it will be coming in July time frame. So this will be one of the largest US academia missions. Of course, summits and all are there, these are the Department of Energy, but this is like anybody can get on to this.
Oh, nice. Nice to know that, yeah.
Yeah, it will be around 35 petaFLOPS.
Wow. So built using what processor?
This is standard, I think the Cascade Lake,
Okay.
Intel Cascade Lake from SDR and our each one. So you can see like these are the kind of very simple downloads over the years we have been like steadily going up and up. This is the software architecture. Okay, so we take care of like from the top level I indicated like we have MPI, PGAS, MK plus X. In fact, we have these libraries you can actually mix and match. Some parts can be written with MPI, some can be written with OpenString. It will run with our runtime. So that enables the application people to really see which programming model is best for not just their application, but which part of the application you can mix and match. So then we support all the networking technologies, as I said, like InfiniBand, IOR, Proxy, Omnipath. These are the kind of features. These are actually our bread and butter of the research. Every time this new technology comes, there are some new mechanisms. My students and I, we actually work on saying how do we take advantage of it. This is where we publish. Then in 6 to 9 months, we actually take that into our open source stack. And many people might not be knowing the complexity, and it's very hard to do it at a university, but I have like almost 200 servers in my lab trying to continuously do QA. Okay, so we have like several staffs, dedicated staff members, continuously running QA tests, and then so that we make sure that we have capability these days. If you do a check-in, in 36 hours we can find out whether that patch is working or if that design is working or not. And if not, again we go back, fix it. And then when the code is stable, this is where we push it, and this is where all the OpenHPC and Sushi, they take it, and then people can just download and it runs. Kind of thing. So I mean, it is not easy. It's trying to do in an academia, but I have been fortunate to have a lot of nice students and staff who are continuing for the last 19 years to do this. And same thing also happens here with respect to different architecture. And today, since it's focusing more on the OpenPOWER, I'll be talking more on that. But we also support like the Xeon, ARM, NVIDIA. I'll be talking a little bit more. We also had a Xeon 5 version, but again that has phased out kind of things. So this is where like there is a basic version of MRPs 2, and then we have an MRPs 2X. This is the PGAS, and then there are some advanced features. Then this is a GPU. So I'll be trying to talk to all three of them. And then as you can see, like over the years, as the OpenPOWER came, Moish actually was one of the earlier academic member kind of thing. So through that, we were able to actually enable all these supports. So if you have an OpenPOWER system, you should be able to download and run these things. These have been supported for the last 2-3 years. So I'll go into a little bit more details, trying to say, okay, just to give you some performance numbers, okay? Because that's what is very critical. I mean, when you design different libraries, how do you distinguish them? Which library does better than? So I'll try to focus a little bit on point-to-point, then CMA-based collectives, I'll go into that, then experiment. These are very new designs we are trying to put together, and then I'll talk about how we have done a very tight integration of the MPI world with GPUs. We call it CUDA-aware API. I don't know how many of you have heard of that term. We actually started that in 2011, the classic IC people introduced that, and now all of the API libraries are using that concept. So this is trying to give you some performance number. Again, I don't want to offend anybody here. I mean, I believe people are here. I'm just giving you academic talk, okay? But this is what you will get. I mean, so this is trying to show intra-node point-to-point performance on OpenPOWER. So if you within the socket, I have 2 cores, and MPI level, I can actually, these are our MAPs, the latest release we made 3 weeks back. This is the Spectrum MPI. 220 nanoseconds. 220 nanoseconds we can send data within 2 cores at an MPI send receive. So these are like the latency. That means half of round trip. I can send it from one process to MPI send, the other guy is trying to do MPI receive and sending the data back and half of that. So then there are some intra-socket bandwidth, there are some curves here. Many of you might have seen these are like tuning. You can, for a given platform, you can tune some of the parameters to get different values. The large message latency, then intra-socket vibration bandwidth. So then this is across the over the InfiniBand network. Here we lose out a little bit in this small message cycles, but you see the large messages we win significantly. And in fact, a lot of these deep learning jobs these days, if you would have done the profiling, they are focusing on large message collectives. So this is where we are trying to enable these next generation applications. So that's what also here you will see. This is the bandwidth. The higher is better. You can see like this is the internode. We are able to go up to like very high bandwidth here and bidirectional bandwidth. There's a very big gap between what we can provide versus what Spectrum MPI can provide.
So that's a good input for a Spectrum team in IBM. Probably I'll share the slides.
I'm sure they know all this. They know all these things. Whenever I present something, all over the world we look at all these numbers. I get a lot of hate mails also. Over the years, a lot of people have become enemies. Okay, but we do it from university levels. We currently show the numbers, and that's what people should see. But yeah, please feel free to say it. But I'm sure it's the same. So then it is not just the point-to-point, as I said earlier, like as the number of cores are increasing, when a lot of communication is happening, like going out or coming in, that is also a big metric. So this is where like we have multiplayer latency. In fact, all these numbers, we also have something called OSU micro benchmarks, MPI micro benchmarks. So when we started this project in year 2000, people didn't know how to measure this. So people knew how to measure application based number. They didn't know how to measure the MPI level number. So we introduced actually OSU micro benchmarks, and that has become very common. These days, even if you see bidding procurement, people refer saying, okay, give us the OSU MPI micro benchmark results, and that has become like standardized. So every time we put some new features, we also correspondingly put the benchmarks. Okay? And then also we get a lot of emails, notes from all different vendors. Can you change that parameter, change that parameter? We don't do that. Right? Again, no offense to anybody, because see, if you do that, then that's not fair. Okay? So we try to put it in a very generic manner. Of course, you can revise it and present yourself, that's fine, but when we somebody downloads from our website, this is a very standard version, and there is a technical reason behind that why we do those benchmarks. So this is where you see, like again, when a multi-pair latency is intranode, like at 20 ppms, 20 processes per node are running. Here again, 2 nodes, 20 ppm. So we are again comparing with not only our MRBase2, Spectrum MPI, OpenMPI. So then there is a newer version here, and this is called an XP-MEM. How many of you have heard of this? Now, this is a newer module Sandia developed, and it provides very fast communication within the node. It is a kernel-based support. Okay, so that means if I want to do communication, I just register it to the kernel, and through the kernel it gets transferred very quickly. Okay, so it's a true zero copy kind of things you want to do. So that's what actually boosts the performance. You will see quite a lot later on. So here you can see we can give you like even for small messages like a 45%, 48%. Even for large messages, we can also give benefit here. Then the same thing also happens multi-pair bandwidth. Okay, a lot of communications are going from one node to the other node. How fast I can start moving, and this is what we see. The higher is better. You can see like almost we can give you almost a factor 1.6, 1.8x higher than the other libraries. So then this is another another thing called CMA. Collectives, I think many of you know. I mean, that is like a lot of scientific applications use broadcast, reduce, alt-wall. These are to be designed in a very sophisticated manner, but the question is, what is the underlying mechanism? Okay. So many years back, in fact, we had this, in our web page, a lot of people did, we did a kernel-based solution that was called Limit. But over the years, it has been actually adopted in the standard data Linux. They have the new name called CMA, cross-memory attach. Okay. So same thing again, within the, I can register the buffer with the kernel, and then the data transfer takes place. Okay. So that's why you will see, like if I can do like this CMA-based intra-node reduce and alt-wall, you can see I can improve by a factor of 3.6, 5.2 kind of thing, that is reduce, alt-wall. Here again, it's a multi-node reduce and alt-wall kind of things, factor of 12, factor of 8.5x kind of improvement. And this is one of the important things, as I said, the number of cores per node are increasing. So when you run a job, you will see a lot of communications are happening within the node. If you don't optimize those, you will not get very good performance at the top. Okay, so this is where we are investing a lot. Any questions? So then the CMA was the first thing, then the experiment is the next generation. So this is what came from the Sandia. This is a further copy, tries to reduce that. And this again, all these are available in our releases. So here again, you get much more benefits, and especially we focus on all reduce, because I think you might be knowing all the deep learning applications, all reduce is the killer. If you can improve the all reduce performance, your deep learning jobs will run faster. Okay. And here we try to do for all the different message sizes. So here we are showing from 16K to 128K to this just to 2 megabytes. Here you can see like we can improve by 2x, 34%, 48%. I'll share this slide so you don't have to remember all these things. So then this is again the optimized, which already used with the experiment. This is across the nodes, like 4 nodes, 3 nodes kind of things. Very similar storyline like this. Then the question is, okay, what happens at the application? So we have also done this mini AMR application. So here you can see just this basic, if you make communication faster within the node, that is the experiment, at an overall execution time, here you see like a process per socket is 10, plus per node is 20, up to 60 process job. I can give you execution time benefits of 40%. Because each communication is happening faster, and that is being translated into the upper layer. So then let me talk about this MPI with a GPU. So this project, as I said, I told you like CUDA MPI. So if you think of like a very simple, how many of you have done CUDA programming? Okay. Most of the time, what you do is like if I have some data in the GPU buffer, I do a CUDA main copy to host. Then I do an API send to another node. The other side do an API receive, and then I copy that. Okay. So it is a very good, like a productivity tool, but if you see the data is moving quite many steps, so you may not get very good performance. So this was in our 2011, we had a paper at ISC. So we asked the question that, and that was the time when this new GPU direct RDMA concept started. So that's what the GDR stands for, GPU direct RDMA. So that means if the GPU and InfiniBand, they are sitting in the PCI bus, I can actually move data from the GPU buffer to the InfiniBand and it goes to the switch. It doesn't have to go through the host. Okay. So we use that, we actually published a lot of papers, then NVIDIA people approached me saying, why don't we take all these designs and push it into the public. So we did that. Look at this number, 1.85 microsecond. I can send data from a GPU, this is a small message. GPU of one node, the GPU of other node. It's not on the same node. Over infinite. 1.85 microsecond I can send data. Okay. And not only like I improve on this, I also improve the bandwidth, bidirectional bandwidth in a significant manner. And I'm very proud of my team who did all these designs. And even though now you go and look at any other MPI library, nobody is able to do this. 1.85. So typical infinite latency is 1 microsecond. In another 850 nanoseconds, we are able to move data from GPU to GPU over the internet. So that gives a big boost to the application. So for example, this is a Humdi Blue, this is a molecular dynamics application. If you use our basic MAPIS 2 versus this optimized GPU direct RDMA version, It's the higher is the better, aggregate time steps, so you can see factor 2x improvement. And more importantly, this is our flagship project. I don't know how many of you have visited Switzerland in the last 3 years. Okay. So, or if you're visiting, if you open up your iPhone and see the weather, we are actually driving that. Okay. So we have a 3-way collaboration with funding from Switzerland Supercomputing Center. This is where like their system is sitting. Meteo Swiss, which is their weather forecasting agency, and then we are trying to provide our HPC. So this is a 3-way collaboration. We are trying to do real-time weather prediction in Switzerland because it has this kind of capability because they want to squeeze each and every cycle out of the machines to have better accuracy, better prediction. So in fact, this is something new which has not gone. In fact, we are trying to work with them because a lot of these weather models also have a lot of data type processing. How many of you know this data type? Okay. So typically, like let's say you have some data, might be some sparse data. Okay. Along the rows and columns, many times what they do is GPU has the data, they take it to the host, then they do some copy to a contiguous one and then send. So what we have done actually, we have done GPU-based kernel to do data type processing. Okay? Because data is already there in the GPU, why should I move to the host? I can launch a kernel to do the data processing and then the data gets moved. So on the sender side we will do the packing, receiver side we will do unpacking, and now we are almost like trying to improve by this is like a mail communication, this is that Osmo model factor of 10 improvement. So we are working with them to see how this will lead to again the next generation of their code. So this is the data from like the Summit kind of system, Summit, Sierra and all, where we have NVLink and Volta. So this is where you will see intra-node latency, small, large, inter-socket. And here, more importantly here you will see like we are able to go up to intra-node bandwidth up to 62.7 gigabytes per second. So we are able to almost saturate the NVLink through our internet. And of course on this machine, the GDR copy, that is a module which is not there, so that's why we don't get good latency. But if anybody downloads that, you should be able to get very similar numbers, like what I showed. So again, here also similar kind of things on the GPU side we have done. Again, optimized already used with XPMN. Similar kind of numbers we see 4x, 2x kind of benefits. So if you want to use it actually, so I'm just trying to provide you, as long as you have a machine with a InfiniBand or OpenPOWER or GPU, you should be able to just download our stack. You don't have to be root, nothing. So we have this community so that you can just download. These are the different libraries requirement. There is a GDR copy library. Then we have a very detailed user guide also. And then just follow that step and you should be able to configure your system. These are all the different kind of installation steps. And we provide flexibility. So if you have a root, you can, we have RPMs. Non-root also you can copy and then put it. Okay. So many people don't know that. Sometimes the vendor tells them, no, this is the library, you cannot touch it. You cannot change anything, but that is not true. Unless you have signed an agreement with this vendor, that sometimes it happens. But otherwise, if you have this kind of machines, you should be able to just download our stack and then run without any issues, and you will exactly see this kind of performance, what is shown. Any questions on the API project?
So is it on top of an MPI or is it a complete replacement of an MPI?
This is an MPI. So this is the MPI
So
itself.
you would just not, you don't need OpenMPI under the covers?
No. This is our library. You have just to on GPU plus OpenPOWER you can run, or x86 OpenPOWER, x86 GPU. All combinations will be provided.
So you are taken the open source to MPI and developed a lot of features on top of that. Is that right?
Let me clarify that. So I think there are multiple versions. The one version is open source.
Yeah.
Others are binary,
Yeah.
but publicly available. Anybody can use it. Okay? Because the thing, what happened is, you put some design in 6 weeks. I can tell you, 6 weeks, another API library exactly comes with same features. Okay? No, I'm not. This is what the world is happening. So that's why when I said that 1.85, so this is the open source, but these are binaries.
Yeah, that's right.
Binaries. Okay.
Yeah,
but you can download. You can download and
I
use
used to work on
Miners
long
for
around
OpenPOWER.
OpenPOWER, yeah. We also have x86.
Yeah.
Yeah,
Which-
OpenPOWER, yes. All these are.
Okay.
So that's why the kind of numbers what I showed, other MPI libraries are not able to catch up. Okay. Because it's a binary distribution. But eventually, I mean, there are a lot of smart people in the world. I mean, we publish papers, okay? I mean, you put an engineer, and you know, put a smart engineer for 6 months, I'm sure he or she will crack it. And
Jonathan, do you have any comment on this actually? You're one of the users of MPI, right? I mean,
So we, so I've played a lot with the Envabish too. So far.
okay.
you have used that.
Yeah.
Yeah.
Envabish too.
Yeah, you can use these other versions also depending on your other configuration. So we are trying to keep like a MIBIS2 is a basic one. MIBIS2 X actually gives you very good performance compared to the other one. It's a one level up. And then this is purely for GPU, but in another might be 2020 we'll try to combine this. So we'll have two versions. One is open, another is closed.
Okay.
So you can, the closed will have more features, more performance. So depending on what you want to use, you can. So that is the kind of the basic MPI stuff. Then of course the deep learning is the next one. And as many of you know, I mean the deep learning, there are two kinds of challenges happening. Scale up. That means if I have put multiple GPUs on a single node, how I can take advantage of that. And then the scale out. That means I go to the outside. And here again, there are different solutions are happening. MPI is one way. I think you indicated that. People are also trying to go through Hadoop, gRPC kind of things. And of course, NVIDIA is pushing a lot on these nickel 1, nickel 2 kind of things. Of course, people want to reach at this best scale up and best scale up. So I'll show you some next few slides how we are trying to enable this community, and not only just by efficient runtimes, but also trying to do a lot of co-design. There's a lot of these frameworks, if you see TensorFlow or Caffe, think of them. Those are just applications for HPC people. These have come from AI people, they don't have much knowledge on parallel processing. Okay? So in fact, you can orchestrate those kind of communication much more faster. Okay? Just think of that as like a demo. So you can schedule it properly, you can map it properly. Then it's not the end job, it's just a framework, but the framework is kind of an application for the lower level players. So we are also working on that. So just, this is how many of you are familiar with Harvard? That is like one of the emerging one which is coming. And Harvard Stack, if you go, it provides you choices, different API libraries you can hook up. Okay? So this is where we are saying, this is our latest MIBIS to that GPU version. If you try to put, you see, this is the thing. You come to, compared to basic MIBIS 2 version, you get much more higher performance, like 11% faster, and almost near ideal, 98% scaling efficiency.
So just a question about the title. So you're saying CUDA where MPI. So how can I envision this as a programmer? I just write the CUDA kernels, and then the scale out is automatic.
Yeah. So let me explain. So there are multiple steps. Of course, you have to put your scientific applications too. Means your application, computation. You have to do your kernel, the CUDA kernel. Okay. But the communication, as I said, typically people do CUDA and copy.
Right.
And then do, instead of you do, just MPI send and MPI receive from CUDA. That's all. Your application will need to make some changes.
Yeah, I think my question is more about if you scale out over multiple nodes, right? Do you have to write any? You have to modify this on your host for your host code.
No.
You have to implement this. No. Okay.
No. See, what I'm saying is always like, let's say, actually I had a slide I dropped it because maybe I'll discuss it offline. So typically what happens for the communication, you do your computation, then you do a CUDA and copy, then you do an MPI send from the host, other side you do an MPI receive from the host, then do another CUDA and copy. You don't have to do that. Instead of that, you just say MPI send from the CUDA buffer. On the sender side, receiver side, you just do MPI receive from to the CUDA buffer, and everything else MPI library. You don't have to. So you have to make a little bit of changes. But it will be much more. You will get high performance and also very good productivity. So then this is where we are trying to keep track of, like especially all reduce is the performance is very critical to to all the deep learning applications. So here we compare it with the Baidu. Baidu is gradually going down, but then also we compare with OpenPOWER. So there is a lot of debate. Currently, of course, a lot of people focus on these large message cycles, the deep learning, but there are also people are rethinking that, okay, there was a classic paper from Datacentres saying if we modify the model and all, it's not just it will become communication bound, but it will become like we can take advantage of short and medium message cycles also. So that's what we are trying to do. So when we design an algorithm, we try to take care of every message cycle. So we give the best performance to all message cycles. So irrespective of how your neural network model is running, at what message cycle you should be able to see good patterns. So then this is like a NVIDIA's Nickel 2. So we are actually, if you see the compared to Nickel 2, we are able to actually perform even better. For all these short messages, we can give you 3x better or reduced performance. Even for very large messages, 20% benefit. Okay. The reason is, like, if you go to any API library people, they have been optimizing all these collectives for the last 18 years. Okay. So we have the knowledge, and so many algorithms are there, and based on the processor, number of cores, system, we know how to optimize it. Okay. So if you simply use the API-based collective, you should be able to gain even better performance than this Nickel 2 people are trying to push from NVIDIA. This is on the latest in the DGX2 machine. So same thing, all reduced operation. So if you see, like, this is on a, I think 8 process or 16 process. I think. No, 16 process. So you can see, we can give you like a short message almost 2.5x better, medium messages 1.7x. We lose a little bit still on the larger message size. So trying to optimize. So the broad idea is that you don't have to stick to any vendor-specific solution. You are welcome, but there are other solutions are out there. You can, if you want to extract more higher performance, you should be able to. As an end user, this is nothing. We just have a DGX2. We put our MMS library. This is actually taken from the Pittsburgh Supercomputing Center. So they have a DGX2. Just as an end user, you just download this stack and run it, and this is the kind of performance you see. So this is where, like, the training. That's what we are trying to see. Like, this is a ResNet 50 training with TensorFlow. DGX2 node, there is 8 voltage GPUs here. So you can see, like, I can give you 7.5% better. But the more important thing is you get very good scaling efficiency. This is as with our solution, which is the red one, you get very good better solutions than the Nickel 2. This is the Nickel 2.3. I think they released a Nickel 2.4 3 weeks back, so we are not comparison with that. So then, as I told, we have done some code designing. So in fact, we have taken the cafe. So we have a version called OSU Cafe. So that is a project, we call it HiDL, High Performance Deep Learning. So we are trying to bring HPC and deep learning together. You can actually try to download this. This is a 2-year-old work. We presented at the PPOP conference. But that time, like in the 2017, we were able to go into 128 GPUs. If we were struggling with 4 GPUs and 8 GPUs, we were able to show to 128 GPUs.
So, that one, did you run it using IBM's NVLink platform?
No, not yet. So this is a little older. This is X86.
Okay.
It's not OpenPOWER.
Okay. Yeah, this could be a candidate for NVLink actually.
Yes, means with NVLink we should be those things. So what we did is, since we had that project running, we took a lot of knowledge from layer 2. It's not the code. Code you cannot move because they are all Java based and all. So here we have RDMA for Apache Spark, RDMA for Apache Hadoop 3.x, 2.x, Kafka, HPC, so all the big data analytics stacks we have actually converted into. When I say RDMA, it's a generic name, but it's not just like you make the calls and distribute to RDMA. We have not done that. It's a totally designing of the stack to get the performance. So currently these are being used by 300 organizations. You can actually go to here, IBD, High Performance Big Data. So again, we combine HPC and Big Data together. We have around like 29,000 downloads here. So here we have like, these are for InfiniBand, Rocky, Ethernet, support for both x86, OpenPOWER. We also have cloud support for Singularity and Docker. So depending on your platform, you should be able to actually download and use it. Just like this project, again, here you can see there is a steady rise in the downloads. So this is what is an architecture. Just for one I show, like Apache Hadoop 2.x. So those of you know the internal Hadoop, we have a HDFS, that is the Hadoop Distributed File System. there's the RPC, there's a MapReduce. So each one of these we have like enhanced it, like trying to use the RDMA. So it is actually running on at the works level, all these stacks. Okay. And not only that, we have actually done integration with Slurm and PBS, and these are the two common schedulers being available on most of the machines. So you should be able to just download that as some scripts. So if you're using Slurm, just put your Hadoop distribution, and you can make a module available just for the end users. So the end users, like if you're a supercomputer center managing a supercomputing center, you don't have to, all your users don't have to go through all the round road steps and all. You just make it a module, make it available, and people can just use it. Okay. So that's what we have, like a Apache Hadoop 2.x distribution. And here again, one thing to note that we don't change any APIs. These are all happening at the networking and IoT, because many times you change the APIs, you may get some good performance, but then you break the compatibility issue. So when we say, like, let's say our release is 1.35, it is based on Apache Hadoop 2.80. So if your application is running with Apache Hadoop 2.80, it is guaranteed to run with our release. So in fact, we make sure we do that testing and all before we push the release. Okay. So it's transparent to the end application stack. So you don't have to make any changes. So now how much performance you see. So this is where the big benefits come. So what I'm trying to show here, in fact, all these stacks, Apache stack or something, if you go through the public version stack has the lowest layer is TCP. Okay. And those of you are familiar with InfiniBand supports a mode called IP over IP, like TCP/IP emulation over InfiniBand. So you can actually run it on that stack, but that may not be very good, may not deliver the performance. So that's what we are seeing here. So the orange or the yellow kind of thing, orange yellow line is the standard stack, whatever you download from your Apache Hadoop distribution, running over it, your InfiniBand hardware, but it is going through your IP over IP. But this is our stack, the red one, and this is a throughput. These are like the different modes are there, so you can see exactly on the same hardware. We are not changing; it is just changing the software stack. You can get a 2.x, 2.2x, 2.6x performance. Okay. So we are not telling you like buy a new hardware or something. You have an InfiniBand cluster. It's a question of which software stack you want to use there. Same thing here. This is on the OpenPOWER again. This is available in the OpenPOWER. So here you can see, like, compared to this different mode again, performance of Hadoop, you can deliver like different message sizes, data sizes, 41%, 55% improvement. This is also the another data point. AMJ you can get like a 12%, 21% benefit. This is the TerraSort execution. So the end objective is here is that you have the hardware, but the question is what software you want to use. Okay. If you use the right software, then you can do. And this is where again I indicated, so you can take our stack just like in API library you download, and there are so many parameters, you tune them for your current machine. Same thing we can do, we have provided a lot of modes based on your cluster configuration, like how much disk space you have, how much SSDs, how you want to configure, put those and give a module out. And in fact, that's what we have been doing. San Diego Supercomputing Center, they are a collaborator on this project. There is a system called Comet at San Diego. So if you are from US and you have an access, these are all installed. So you can just run your Hadoop job, you don't have to do anything. Just if you have an account, you can just run Hadoop cluster using our Hadoop on our system. So same thing we have done for Spark. Exactly the same idea. And here you can see again on the OpenPOWER. This is a group by and sort by results we are trying to show for different data sizes, 11%, 18% kind of benefits we see here. This is TerraSort and sort. You can see 100 gigabytes of TerraSort. We can give you improvement by 35%, 25% kind of things. Because the reason is like we are trying to do the communication very efficiently. Okay, that's the whole idea. We are trying to cut down on the overheads, and also RDMA has the biggest benefit of overlapping computation with communication. That's what RDMA actually is the fundamental thing it provides, and we have restructured the stacks to exploit that, how do you get overlap of computation with communication. And same thing you can do again as Spark job with So if you want to use it, again, I'm just trying to give some 2-page slides. You have a cluster, you want to try our stack, again, you have full control. You can just download this, we have a very detailed user guide, you just follow through this, JDK, for power system you have to install the IBM JDK, and then again, no root privileges are necessary. Many times people think about binary packages, you need to have sysadmin root access, but that's not true. So all our software stacks, any user mode, you can use it, even the K stacks also. If you have access to any user like Samir here and all, that's what I told you, a lot of people use in that kind of thing, they just download and run and use it. And then we have again a detailed user guide, IDM for Hadoop 2.x, no root privileges are necessary, IDM for Spark, exactly the same thing. So only one flag you need to do. We have a flag internally, so it's called hadoop.iv.enable or spark.iv.enable. That's the only thing you need to download, just run it with that flag and it makes sure that you're running well. So these are all the stacks which are being available, a lot of people are using it. So then, since 2 years back, some of the people want to actually have commercial support kind of thing. So a lot of people use that. In fact, for each of these projects, we have actually open discussion list. And in fact, many times we have got feedback that we try to serve the customers or the end user much more faster than even a paid service. Okay. People raise questions, we provide solutions. That is perfectly fine with us, but still some organizations, they have a little bit of itchy feeling saying, oh, this code is coming from university. Okay. So they want like some organization with a legal thing saying, okay, I can sign it and I can have a 1-800 call or those kind of things. So this is what we are trying to provide for the last 2 years. So this is a commercial branch called X-ScaleSolutions.com. So here again, depending on the end users, just like any other ISV, we can provide support for all those libraries if you want. Okay? Or any organization want that, we can do platform-specific optimization, timely support. In fact, different, just like any other software stacks, we have different levels of services. Based on the money, you can get a 2 days response time, 3 days, 7 days response time, and you get a web portal access, monitor how your things are progressing. So for the last 2 years, we are actually supporting the Lawrence Livermore National Lab, all their machines. Okay. Because they are one of the largest MRP users of Lawrence Livermore, all their machines. So through this, we are able to provide very dedicated services to them. And recently, actually, we became the OpenPOWER consortium. Now we are a silver ISV member. I think thanks to Ganesh and giving this idea, and we went through this process. So now actually it totally opens up, and again, our software stacks can be integrated with the other stacks. They can be tested, validated. We can also participate in bidding. It totally depends on your end user. So we are no different than any other commercial IBM or NVIDIA or Intel kind of things. We can play at the same level as the others. So that's the new development I just wanted to say. So to conclude this, what I indicated, like upcoming exascale systems need to design with a holistic view of HPC, big data, deep learning, and cloud. I didn't get time to go over the cloud, but that is also important thing. And especially these are the three things: OpenPOWER, InfiniBand, and GPU. These are the emerging technologies to put large-scale things. And I presented a set of solutions from the OSU to enable this trend. And in addition to that, this commercial branch is also trying to provide the full-fledged support things based on your end users. So if you are an OpenPOWER user here or any other place or your university or something, please feel free to take a look at this, and we'll be very happy to work with you to make sure that you get the best performance and scalability on your machines, whatever you have purchased. Okay. So with this, let me just thank all our sponsors. But more importantly, these are all my heroes. Okay, what I presenting is like an accumulated version of 20 years of work. A lot of new students come, they contribute. These are all the old past student staff. You see their names there with all these companies in national labs. They are working, and these are all the current students and stuff. Okay. So they do all the hard work. I just come and do one of them. but I always try to acknowledge them, saying they are the heroes. Without their hard work, we would not be doing like this. So this process has been continuing, and since I'm in Singapore, this is the first time I'm here. I want to advertise this also. I'm continuously looking for excellent students, staff, kind of thing. So in my group, we have all kinds of positions open: PhDs, postdocs, even programmer. If you want to have your name in the previous list, please contact me. Okay. Thank you. Any quick